Let's go through equal 480 sliding window median. For this question, it gives us integer array nums and also integer k. And it has a sliding window with fixed size k. And every time we want to find the median of this window. So it defines the median. For example, the outer number is just the middle number. And if it is k is even, then that will be the average of the middle two. So it let us to return a double array. So for this question, we know because the k is 10 and then length n is 10 to the power 5 time complexity. So we know we should have some n log n or those kind of approach, time complexity approach. Brute force, it will be TLE. So we're thinking about for this question, we can have two priority queue. One is a min heap and a max heap. So for every time we add a number, the things that we put that into a min heap first, and then um, we add the first step is added to the min heap. Then we pour a value from min heap to max heap. And the third step is that we check if the max heap size is smaller than min heap, then we need to pull one element from min heap to max heap. So this is three steps. So in this case, when we add a number, we can make sure the max heap will have size always greater or equal to min heap. And the max heap, if it is greater than min heap, it will be min heap size plus one. So this is the main concept, but there is some kind of problem for this kind of approach is that because we are using sliding window, we add a number to our data structure that is two heaps. And when an item moving out of this kind of sliding window, we need to delete from those kind of heaps. To delete an item from heap, that is not a log n approach. It is a ON operation, right? So we need to have some way to have the heap delete more efficient. And also for delete operation, right? So also that is add operation. So delete operation is that if we have a way check whether that is in the min heap or max heap, right? If it is in min heap, delete that from min heap, and then trying to see if the min heap is size is smaller than max heap of -1, right? If there are differences is 2, then we pull one item from max heap to min heap. Then also we check if it is in the max heap. If it is in the max heap, then we delete one item from max heap and also pull item from min heap to max heap, right? Because the if we delete we also check, right? If the max heap is, it should be equals to min heap or equals min heap plus one. If it is smaller than min heap, we also pull item from min heap to max heap. So that is the add logic and delete logic, right? But since that we need to have some beta approach for more efficient delete approaches. There is another question called the sliding window string median that does not have delete operations, so it will be much easy. But for this question, it has delete operations. If we use min, use a priority queue, right? It will be O n operation to delete an item. So we have two approaches to do delete efficient. One approach is we write our own heap method, and for this heap method we use a lazy delete. Another is we use tree set to simulate the priority queue for deletion. Because tree set we remove item that is the log operation. So we can go through both approaches. Let's go through the first approach is we write a lazy delete queue. Let's define a class heap. Let's make this as a generic, and we need a private priority queue. So this heap is a wrapper for this priority queue, and in order it to support a lazy delete, we need a set. We put those kind of deleted item. When we delete an item, we put those kind of deleted item into set. And when we do pick or poke those kind of operations, we then we do check whether the top of the priority queue is in the set. If it is in the set, then we pop it. We are going to use another variable called size. Why we need size is that because the lazy operations, right, we cannot use this priority queue size to represent the heap size because some of the items they are not removed. They are removed until we do the lazy operation. So that is we for the size when we we'll add those kind of size and pull we need um we need remove those kind of size and also delete delete we need to when we call a delete function we need to update this size operation. So if because we want to have a size method, right? So just return this dot size. Mm, so let's write the constructor. So that is a public key. So we need to have the priority queue T PQ, and we're going to have this dot PQ equals PQ. And we are going to have delete this dot delete set equals new hash set. And we are going to rewrite those kind of offer message, re-implement those kind of offer message, right? So we know for this offer, we have to have PQ offer this kind of num, right? And the things that we need here to update the size. And also public tick. So for tick method, what we are going to do is that we are going to do the lazy delete operation first, and then return pq.pick, and we're going to have a public T pull. So for the pull operation, we also need to lazy delete and return PQ dot pull. So for this pull, actually, um, actually, um, we should minus the size, right? Because one of the item is removed. Of course, um, you can write this one to delete set, right? And then after pull, then remove from delete set. But for this one, we can skip add to delete set, remove delete set, right? But the size is changed. We need to make sure it is decreased. And public boolean is empty. So for this one, we can write lazy delete and return PQ of is empty. Because if they delete, then PQ is empty. That means all of the items in the top are empty, are removed, right? So we can write this. We can also write um, also you can write a return this dot size equals to 0, right? It will do the same thing. And we're going to implement public int size. So for this one, we'll return this dot size. So for this one, we cannot, this is not correct. We'll make sure this is not correct. This one, this is not correct because for lazy delete, it will just delete those kind of deletable item in the top, not all of them, right? So this is the reason we need a size variable, and we also need to implement delete the no. So this one is because we delete one, right? So we'll have size should decrease, and also delete set we should add this none, right? And also let's write the lazy delete function. Private void lazy delete. So that is when we do this kind of peak or pop operation. We try to see why this PQ is not empty and delete set contains this PQ dot peak. Then we're going to have delete set remove. Also, our PQ need to remove for right for this item out. And when this pull during the pull, the size has been decreased as long as when this is removed. So this will be the lazy delete heap, right? So if we have this kind of lazy delete heap, our delete operation will be averagely O log n operation. So this is the first approach. So that means that we need to have priority queue integer max PQ equals new priority queue. So what we do is that A, B goes to if nonce A equals nonce B, right? So we are going to return integer compare. Then we compare index BA, right? Otherwise, we are going to have integer compare this value nonce B nums A. So that is the priority queue for the max priority queue, and also we need a min priority queue, right? Min PQ. So min PQ, the order is reversed. So that is index A and B, and nums A and nums B. So we use our heap, right? Heap integer. We call max heap equals new heap max PQ, and heap integer min heap equals new heap min PQ. Okay, so what we do is that let's have int n equals nums at length, and double result equals new double a minus k plus 1. So what we do is that we have for loop for int I equals 0, I smaller than n, I plus plus. So we'll write an add function, add helper, add a num, which will have max heap and min heap. And for this one, we put index. And we'll say if this index is greater or equal to k, right? Then for this sliding window, we are able to remove and none, those kind of I minus k from our data structure. So we have max heap, min heap, that's I minus k, right? And we also write if I is greater or equal to k minus 1, right? Then result I minus k plus 1 equals, we'll write another help function called find the median max heap, min heap, and the nums, right? Because we need the values from these nums. And in the end, return result. Here, remove item. Let's also, for the add item, we don't need to pass in these nums. For the remove item, we also pass in these nums, because for this heap, we didn't have a method called contains item, right? So what we do is that we check the max heap, because the index before we remove, we by this code we know they are either in the min heap or in the max heap, right? So we don't need to write our own function in heap to check if our data structure this heap contains index or not. So we just compare the top of max heap, right? So if the index is small or equal to the top of max heap, that means it is in the max heap. Otherwise, it is in min heap. So we pass in, because we need to compare the values, right? So passing the nums. So let's write have it void add number, and we need keep integer for the max heap, and the heap integer we call min heap, and also an index. So for this one, what we do is we are going to have max heap offer this kind of index, right? And then we have min heap dot offer max heap dot pull, right? So after this, we'll say if the max heap the size is smaller than min heap dot size, because we add one item from max heap to min heap, right? So it is possible if max heap dot size is smaller than min heap dot size, then we'll add back. So we're going to have max heap dot offer min heap dot pull, right? So this is the add function, and we're going to have remove function, right? Private void remove num. So we're going to have heap integer max heap and heap integer min heap, and we pass in these nums and also this index. So that means that let's get the max heap at the top. So I equals max heap dot peak, right? This index, and v equals nums I. So we'll say if nums index is smaller than v, right? Or we'll say nums index is equals to v, and index is small equals to I, right? That means this index is in the max heap. So we're going to have max heap dot delete index. And when max heap delete, we need to rebalance, right? So we'll see if min heap dot size is greater than max heap dot size. We're going to have max heap offer min heap dot pull. And here we can write else, right? Because the index is either in max heap or in the min heap. So in the else, that means it is in min heap, and we are going to min heap dot delete index, right? So we're going to have if max heap dot size is greater than min heap dot size plus one, right? Because the max heap there it can be either equals to min heap or equal to min heap size plus one. So if it is greater, then we need to rebalance, have the min heap that offer max heap dot pull, right? So this will be the remove function. So we use this iterate, and this kind of check compare with the max heap top item to check whether it is in max heap or min heap. Use this kind of trick. We don't need to write a method to write contents, right? Otherwise, we need another method to rewrite in this heap. So we have another private double find a median. So we are going to have heap integer max heap and heap integer min heap, and we need to pass this to nums, right? So that means that the max heap size can either greater or equals, right? If it is greater, that means it is equals min heap dot size plus one. So that means the max heap with the peak item, right? Will be our median. Otherwise, we'll get a peak from the two heap, right? Return 1.0 by nums max heap dot peak, and plus 1.0 multiplied by nums min heap dot peak, and here by 2.0, right? So this will be lazy 35. So this will be the lazy delete, right? Um, Besides lazy delete, we can also use because if sometimes it's really hard for us to write a heap class. This will take too much time. Sometimes it will be too meaningless, right? If you just to remember those kind of things. Um, so we can use a tree set to substitute this kind of heap. So if we use tree set, what we need is that the things that there is one advantage when in the delete items, right? We don't need to pass these nums to compare with its top. We just use the tree set contains or not contains, right? So in the tree set, we pass in the index only. Here is the trick. We cannot put an array in the tree set because array contains is checking the reference or memory address, right? So it will have some errors if we use the int array. So we pass in the index into tree set. And the tree set, we compare first the number and then index so that for it will guarantee that for the same value, um, they will not be the same, right? Um, so let's write a tree set approach, right? And in this case, we don't need to write a new class called heap. We just need to use tree set integer. We, we also call next heap equals new tree set. So A, B, um, so if nums A equals nums B, right? Then we're going to return the integer compare B, A, right? Otherwise, we're going to integer compare its value. That is, we'll compare value first, then compare index. So this will be the max heap, right? And we also need a min heap. So we call min heap. And the order is reversed. When value does not when value equals, right, then we first compare this value array value, and then AB is index, then compare index. So this is the tree set. So let's also have and actually for this kind of code, it's the same, right? Nums dot length and double result equals new double n minus k plus 1, right? For in I equals 0, I smaller than n, I plus plus are going to have add now. We also write add number max heap min heap index I. So we'll say if I is greater equal to k, we're going to have remove number max heap min heap, and there should be I minus k, right? And let's say if I is greater or equal to k minus 1, then we're going to have a result I minus k plus 1 equals find the median max heap min heap. We should pass in these numbers, right? Because we put in the heap is index, and then return result. So we also need a add a number, private void add a number. So we now have a tree set as a heap integer, and the max heap, right? The tree is set integer min heap and index, right? Because we are adding to the tree set that is index. So we have max heap add index, and then we have min heap add max heap dot pull. In tree set we call pull first. Then we'll say if min heap dot size is greater than max heap dot size, then we're going to have max heap add min heap dot pull first. Right. So this is add number, and also remove number. Private void remove number tree set integer max heap and tree set integer min heap int index, right? Because this is set, right? Tree set. So we can now we just a moment ago, there is no good way to check whether that is contains or not, right? So now we can just use contains method, right? So a moment ago we compared that number, we're passing the number to compare with the top or the max heap. But now we just write it for max heap contains index, right? Then I'm going to have max heap remove index, and then we'll say if max heap dot size is smaller than, because we removed, right? Heap dot size, we need to rebalance, so we're going to have max heap add min heap dot pull first. So else, that means CTC in the min heap. So we have min heap dot remove index. Let's say if min heap dot size is smaller than max heap dot size minus 1, right? Then we're going to have min heap dot add max heap dot pull first. Okay. So this is a remove method, and also private double find the median, and we need to have tree set integer max heap and tree set integer min heap. We need to pass this kind of non-direct because we need to check the numbers, right? So if max heap dot size is greater than min heap dot size, that means that it has one more element in max heap, right? So just return 1.0 multiplied nums max heap. Because this is tree set, right? We use the first. Um, Otherwise, we return one 1.0 multiplied nums uh, max because in this case they are equal. That means there is one in the max heap, one in the min heap, multiplied by nums min heap of first, and divided by 2.0, right? So this will, if we use tree set, right? We don't need to write our own heap class, right? Um, but we may need to be familiar with those kind of tree set its method in the Python code. We let's still use tree set approach, right? We import sorted sorted containers, right? So what we do is that we have max heap equals sorted um, containers. It's imported, right? So that will be sorted set. Sorted set t equals lam x, right? So this is max heap. So will be first by nums x, and then otherwise that will be index, right? And min heap equals should be positive, and we're going to have in the length of nums. So result equals this one multiplied by n minus k plus 1, right? So what we do is for I in range n, we are going to have mm, um, so we'll have add num, add num. Mm, we don't need nums. We just need this, right? And we'll say if I is greater equal to k, we'll have remove num I minus k, right? And we'll say if I is greater equal to k minus 1, we'll have result I minus k plus 1 equals find the median. Mm, yeah, just this one, right? And in the end, just return result. So here, we can define add num, right? So we just pass in this kind of index And what we do is that max heap add index and min heap add max heap of pop there. So length of if length of min heap is greater than length of max heap, then we need to rebalance, right? So we have max heap add min heap pop there, and also remove none, right? df remove none in index. So this one is if index in max heap, right? Then we'll have max heap remove index. So in this case, it's possible the min heap will have large size, right? If length min heap is greater than length max heap, then we're going to rebalance max heap add min heap of top 0. So else that means this index is in the min heap. Um, else. So we can have min heap dot remove index, right? So here we'll say um if length max heap is greater than length of min heap plus 1, right? Then we'll have rebalance min heap at max heap dot top 0. And we need to find the median. Find the median. So what we need is if length max heap is greater than length of min heap, right? So that means it has one more element. Then we just return. We need to change this as float, right? Float nonce max heap 0. Otherwise, what we return is um, float nonce max heap 0 plus float nonce min heap 0 divided by sigma o, right? Line 8. This is add index. What's the problem? Invalid syntax. Add index. this index max heap invalid syntax. Why this is invalid syntax? Index max heap remove number. Do we need a max heap min heap remove? We also need a remove. Let's try to see. Where is syntax? Sorted containers. Sorted set. Sorted containers. Sorted set. Next heap. Add. Oh, there is a comma here. Actually, return line 34. Return result. Right. So this is Python approach. Actually, we don't need these parameters. Doing like this, we'll say no matter you do tree set or use a lazy, we write our own heap to lazy delete, right? Those kind of add, remove items log in up time complexity, and this is ON space, right? Actually, it's OK space because there are always key items. It's a sliding window. Um, for it is O n log k time complexity. Um, and if we write our own heap, our lazy, right, the delete will be averagely log n. It is it will say it's average. It's not a guarantee every time. It is O log n, right?